In today's video, we are going to make a simple AI framework called behavior trees. We will create AI that is going to chase us when we are in a certain range, shoot at us if it gets close enough, and run away to look for cover when its health goes under a certain amount. Let's have a look at how behavior trees look like. For this project, we will use Unity 2019.3. All of the units of the tree are objects of class of type node. Each node has a field that describes the state of the node. Each node can have only one of three states: success, failure, and running. Each node also implements a method called evaluate, which will run every time you want to evaluate the tree and find the proper behavior. In this method, we set the node state field value. Let's see what our tree will look like. The top node of our tree, on which we will call the evaluate method, is a composite node. We will cover two main composite nodes, selector and sequence. Let's take a look at the selector first. Every composite node state is dependent on states of its child nodes. Every composite node evaluates its child nodes one after another. That order is very important. In case of the selector, we are checking each child node until we find one with a success state. When the first node after evaluation has a failure state, we go to the next node and evaluate it. If the next node has the success state, the whole selector node will set its state to success, and we don't have to evaluate any more nodes. Only in a situation where all of the child nodes have a failure state will the selector node also be a failure. Now let's take a look at the sequence node. This node will also evaluate its child nodes one after another, but in the case of the sequence, when the first node is a success, we don't automatically make the whole sequence a success, but we go to the next node. If the next node is a failure, then the whole node is a failure and we don't have to evaluate any more nodes. The sequence node is a success only when all of the child nodes are a success. Now let's take a look at the tree that we will be working on. The top node will be a selector node that will have three children. First, the cover node, which will be a sequence. The second one will be a shoot sequence node. And the last one will be a chase sequence node. Now, in the cover selector node, we will have two nodes. The first will be a health check node. Second one will be try to take cover node. The health node will return success when the AI agent has health under a given value. If the AI agent health is above this value, the health check node will return failure, so the whole sequence will be a failure and the agent has no reason to go to cover and will try to shoot or chase. Otherwise, the cover sequence node will be able to evaluate the next node, that is the try to take cover node, which is a selector. This node will first check if an agent is currently behind cover. So the first child node will be of type Icecovered Node. If this node returns success, the whole try to take cover selector is also a success, and in result the whole cover sequence is a success. If an agent is not in cover, we will evaluate the next child node called find cover. This node will select between two nodes, one that will move an agent to cover if there is one available, and if not, then an agent will chase us. The first node will be a sequence called GotoCover Node, and will check if there is a cover available. So let's add the first child node to the GoToCover sequence and it will be called isCoverAvailable. This node will return success if there is a cover that will hide an agent from the player's side. If so, we will evaluate the next node that will simply move an agent to the cover. This node will be called getToCover. If there is no cover available, then the whole GoToCover sequence is a failure. The find cover sequence will move to the next node, which will be a chase node. Because the nodes are objects, we can reuse already existing nodes and we don't have to construct them several times. In this case, we will reuse the chase sequence that we will discuss in a minute. If the whole cover node returns failure, we can move to the next sequence node called should. This node is a sequence that first will check if the player is in a certain shooting range by isInRange node. If we are in range, then the should selector will evaluate the next node called should node that will make the agent fire a weapon. If the isInRange node is a failure, the whole should sequence is a failure and the top node selector will evaluate the last node, which is the chase sequence node. The chase sequence node will behave similar to the should sequence, but the distance in the isRange node will be different, and instead of shooting we will chase the player. Let's take a last look and let's start implementing our base class called Node. Back in Unity, create a new folder called Scripts. Inside this folder, create another one called Behavior Trees. And inside it, create a new C# script called Node. Open this script. This class will not be a mono behavior, and let's make it serializable to make it visible in the inspector. Also, the node class will be an abstract class. Like we said before, every node has to have a field that is describing the state of a node. So let's add a field responsible for that and create a enum of type node state that will have three values: success, failure, and running. Next, add a getter for the node state variable. And lastly, declare an abstract method called evaluate that has return type node state. Every class that inherits from the node class will provide its own implementation of this method. Back in Unity, let's create another script called sequence. Sequence will of course inherit from node class, and in result we'll have to implement the abstract method evaluate. As we know, sequence is a composite node, so it will have a reference to child nodes that it will evaluate one after another. So let's add a new field that will be a list of nodes. Let's create a constructor for our sequence with a list in parameter. In an evaluate method, we will iterate through all of the nodes and call the evaluate method on them. Each child node evaluation will return the value of node state enum type. Then we will go through that enum in a switch statement. Let's also declare a boolean value, is any child running, that will be true if during any child evaluation we will come across running state. So in case of state running, the sequence does not break. We will just set is any child running boolean value to true and go to the next child evaluation. If any child is a failure, that means that the whole sequence is a failure, so we assign the failure state to the node state value and return it, which will in result break us out of the method. If the state is a success, we don't do anything and we can evaluate the next child. After the loop has finished, we are sure that none of the child nodes was a failure, otherwise we would have never reached this line of code. So what we have to do is to ask if any child was running. If yes, the sequence state is set to running, and if not, we know that all of the children nodes were a success, so the whole sequence is a success. And we return the node state value. Now, back in Unity, let's copy the sequence class and change its name to selector. This class will be pretty similar to selector class, so we will save some time. First, be sure that you are in the selector file and change the name of the class in the declaration and the constructor to selector. Let's clear the evaluate method and leave the for loop and empty switch statement. In the selector node, if any of the child node evaluate methods return running state, that means that the whole selector also sets its node state to running, and we can return out of the method. We do the same thing in case of a success state in any of the child nodes. In case of failure, we do nothing and go on to evaluate the next child. After the loop ends, we are sure that all of the child nodes were a failure because we didn't return out of the method, so we set the selector state to failure and return it. There is one more very useful type of nodes called decorator nodes. Those nodes take a node and modify their state. A very popular decorator node is called inverter. This node takes another node and flips its state from success to failure or from failure to success. For example, our isInRange node will return failure if the given distance is bigger than x. But what if we want a node that will return success in that case and we don't want to write another node? We can just pass the isInRange node through the inverter node and get this behavior. So back in Unity, let's copy the sequence node file and change the file name to inverter. Open this script and modify it similar to what we have done with the selector script. The inverter class will have a field with only one node that it will modify. Let's fix the constructor as well. Don't forget to change the class name. Because we don't have a collection of child nodes, we don't need to use the for loop. We will just switch by the result of the evaluation of our single child node. In case of state running, we don't change anything and the inverter also sets its state to running. If the child node state is a failure, the inverter is a success, and if the child state is a success, the inverter is a failure. Now that the main framework of our behavior tree system is ready, we can start implementing custom nodes. So let's create a new folder under the scripts folder called nodes. In this folder, create a new C# script called health node. Before we start any coding, let's prepare the scene first. So add a plane to act as a ground object, then add 2 cubes for our player objects and for the enemy object, and lastly add separate materials for each of them so we can know who's who. On the enemy game object, add a new script called enemy AI. That script will connect the enemy game object to the behavior tree and will provide the tree with necessary data. Let's implement our first custom node. The health node, like every other node, will have to inherit the node class and implement the evaluate method. The health node will have a reference to the enemy AI component to get the current health value of an agent, and a float called threshold that will be a value to which we will compare the agent's current health. Let's generate a constructor with those fields. In the evaluate method, we will simply return success if an agent's current health is lower than the threshold assigned in the constructor, otherwise we will return failure. There is no situation where we're returning a running state. I forgot to assign the calculated state to the node state field. This won't be a problem because our composite nodes, which by the evaluate methods return value and not the node state field of the node. But nevertheless, that is a mistake on my part. We don't have any enemy health yet, let's add it in the enemy AI script. First, let's add a serialized field float for enemy starting health, a private float for enemy current health, and in the start method initialize the current health with the starting health. Now add the getCurrentHealth method that will simply return the current health. Next, add 2 more serialized fields, one that will describe what health amount is considered a low amount, and a flow that will tell us how fast the enemy will heal. In the update method, we will add points to the current health value equal to the speed assigned in the inspector multiplied by the time passed in this frame. Let's also make the current health a property that in a setter will clamp the current health value between 0 and the starting health. Now let's start working on the next node, so go back to Unity and create a new C# script called range node. Open this script. The range node will need to know what range we should compare the distance to, a transform from which to calculate the distance, and this will be our enemy, and a transform to which calculate the distance, and that will be our player. Let's generate a constructor with all of the class fields. Of course, the range node inherits from node class and implements the evaluate method. In the evaluate method, we will first calculate the distance from the origin to the target. Next, we will return success if the distance between them is equal or less than the specified range, otherwise we will return failure. No running state is possible in this node. Don't forget to assign the calculated state to the node state field like I forgot to do and like I noticed before. In the enemy AI script, add two fields that will define the range in which an enemy should start shooting at player and start chasing him. We also need a reference to the player transform for the range node constructor. Go back to Unity and create a new C# script for the new node called Icecovered Node. Open that script. This node will need a reference for the transform of the player and a transform of an enemy. Let's generate the constructor for this class. And again, inherit the node class and implement the evaluate method. In the evaluate method, we will raycast from an enemy position, in this case the origin position, in direction of the player, in this case the target. If we hit something, we will ask if that hit object is our target. If the answer is no, that means that there is something separating us from the player and the enemy is covered and will return success. Otherwise, we return failure. And that's it for this node, so let's go back to Unity and create a new script for the next node called Chase Node. It will also inherit the node class, therefore implement the abstract method evaluate. First, we will need a reference to the player transform called target. Let's add a Unity engine.ai namespace because we will need a reference to a nav mesh agent component of an enemy. Let's generate the constructor. In the evaluate method, first we will calculate the distance to the target. If this distance is greater than some small value, then we will start the agent, set its destination to the target position, and return state running. Otherwise, we stop the agent and return success. We do the distance comparison in order to stop an enemy object from getting too close and overlap with the player object. Let's go back to Unity and create a new script for the next node. This time it will be a shoot node. In this node we will need a reference to a nav mesh agent component, so add the Unity engine.ai namespace. Also we need a reference to an enemy AI component. As always, inherit from the node class and implement the evaluate method. In the evaluate method, we could instantiate some projectiles and so on. But to save time, we will just change enemy color, which will indicate that an enemy is in the shoot node. We will also stop the nav mesh agent. This node state will always be running. So back in the enemy AI script, declare a setColor method with color as a parameter. We will need a material reference, so let's add it and initialize it in the start method. In the setColor method, we will simply set the material's color to the one provided in the parameter. Let's also change color when an enemy is in the chase node. To do that, we need to add a reference for the enemy AI in the chase node. Back in Unity, create another script for the isCoverAvailable node and open this script. As always, inherit from the node class and implement the evaluate method. This node needs a field that will be an array of all available covers to choose from. We will create the cover class in a second. Also, we need a reference to the target transform, so the player's transform, and an enemy AI component. So let's go back to Unity and create a cover object. This will be a simple cube scaled to represent a wall. Next, create a new script called cover and open it up. Each cover will have a reference to the transforms, which will be children of the cover object and will represent spots to which an enemy can move when moving to the cover. Let's add a method to return those spots. Now move the cover script to the right folder and attach it as a component to the cover game object. Next, create an empty game object under the cover game object and call it spot. Move it a little to the side of the cover with the forward vector pointing towards the cover. Next, copy it and move it to the other side of the cover. Rotate it 180 degrees so that the forward vector points towards the cover. Now duplicate the cover game object multiple times and create a kind of a level layout with them. Let's go back to the isCoverAvailable node and the evaluate method implementation, but first create a constructor for this class. The evaluate method will first try to find the best spot to cover an enemy. It will return success if it finds one, otherwise it will return failure. In the findBestCoverSpot method, we will iterate through all of the available covers, and in each cover we will pick the best spot. We will define a spot as being the best when having the lowest angle between its forward vector and the direction from this spot position to the player's position. We could also take the distance from the enemy to cover into consideration, but for simplicity's sake, let's only care about the angle. So in the for loop, we will call a method called findBestSpotInCover that will take a cover as parameter and an angle as a ref parameter. If the current cover finds a better spot, then it will assign this spot to the best spot variable, which will be the return value. In the findBestSpotInCover method, first we will get all spots in this cover and iterate through them. Let's also declare a variable for the best spot. In the loop, we will first do a check for this spot with check if cover spot is valid. We will get to this method in a second. If the spot is valid, we calculate the angle between the spot's forward vector and the direction to the player, so to the target. Let's cache the direction in a variable. If the angle is smaller than the previous smallest angle, we will assign the calculated angle to the minimum angle variable. Here we can see why we needed a ref parameter. Next, we assign the current spot variable to the best spot variable. Also, the direction value has to be calculated inside the loop, not outside. And calculate the direction not from the cover's position, but from every spot's position. Now let's discuss the check if spot is valid method. So before we even calculate the angle, we have to know if in fact an enemy will be covered from the player. We will check it by performing a raycast from the spot's position in the target's direction. Of course, in the place we are checking if the cover is valid, we should pass the spot, not the cover, in a parameter. Also, I named it check if cover is valid. I don't know why, but let's call it check if spot is valid. If we hit something in the raycast and it is not the target, then we consider that spot valid. We could pass the cover reference in the parameter too and say that the cover is valid only if raycast hits the cover. It would be a better solution because right now we can hit another enemy and the raycast will falsely tell us that the spot is valid. Now back in the evaluate method, after we find the best cover spot, we will set it to a variable in a enemy AI component that we will create in a second. So let's add a method in the enemy AI class called setBestCoverSpot. Also add a reference field for that spot. And in the setBestCoverSpot method, just assign the parameter to field variable. In the enemy AI script, let's add an array field that will hold all available covers. Back in Unity, let's create the last node called GotoCover Node. It will be similar to the chase node, so copy the chase node script and change its name. We could even use the chase node here or think of some more generic solution like a GoToPosition node, but let's leave that for now. Open the GoToCover Node script and change the class name. We will not need a reference to the target, so remove that field and the corresponding parameter in the constructor. The difference between this node and the chase node is that we won't set the navmesh agent's destination to the player's position, but to the best cover position that was found in the Icecovered node. Let's add a method to the enemy AI script that will return that spot. Next, check if the spot is not null. If it is, return failure, otherwise set the destination to the spot's position. Now let's construct a behavior tree in the enemy AI script. First, add a reference to the top node, and in the start method call the construct behavior tree method that we are going to implement right now. Let's bring up our tree graph to help us create appropriate nodes. We are going to start with the custom nodes and later the composite nodes. So first let's create the Icecovered node and pass the appropriate parameters in the constructor. The next node will be the GoToCover node. For this node we will need a reference to the navmesh agent component, so let's add a field for that. Also add the UnityEngine.ai namespace, cache this component in the awake method. Back in Unity, add a navmesh agent component to our enemy game object. Next, select all of the covers and the ground object and mark it as static. Next, go to the navigation tab and bake the navmesh. Now that we have the navmesh set up, we can finish creating the GoToCover node. The next node will be the health node. Next, create the Icecovered node. Next, the chase node. Next, the two range nodes. First one with the chasing range in the parameter. Then the second range node with shooting range in the parameter. Then the shoot node. Now that we have all of our custom nodes ready, let's start assembling them in proper sequences and selectors. We'll create them from right to left and from the bottom to the top. First, let's take care of the chase sequence, so create a new sequence that in its parameter will take a list of two nodes, the chasing range node and the chase node. Now create the same kind of node for the shoot sequence, but initialize the list in parameter with the shooting range node and the shoot node. Then, similarly, create the GoToCover sequence that will be initialized with a list containing the Icecovered node and GoToCover node. Next, create the findCoverSelector node. The list in the parameter will be initialized with the just created GoToCover sequence and the chase sequence. Here is an example of reusing the already existing part of the tree. Next, create another selector for the try-to-take-cover node. We will initialize the list in the parameter with the findCoverSelector and Icecovered node. Now we can see why we need to create nodes from bottom to the top. The higher nodes need to be initialized with lower nodes, so we have to create those earlier. Now create the main cover sequence and initialize it with the try-to-find-cover-selector and the health node. And in the end, we can create the top node that will be initialized with the main cover sequence, the shoot sequence, and the chase sequence. As we can see, constructing bigger trees would be a really tedious process if we did everything by hand. That's why almost all behavior trees frameworks use node-based editor windows that create nodes in a visual editor. That is out of scope of this video, but if you would like to see something like this, please let me know in the comment section. Now in the update method, we will call the evaluate method on the top node. We could add some interval value so that we don't run the tree every frame, but let's leave that for now. We will also check if the whole tree returned failure, which would mean that all of the child nodes returned failure. In that case, we will change the enemy color to red. Quick fix with the current health property. We forgot to declare a private field for current health. Let's also remove the getCurrentHealth method. We don't need it anymore. We can access the current health from the property. In the enemy AI script, let's also add the onMouseDown method. This method will be called each time we click on the enemy object, and we will damage the enemy by 20 points. Now go back to Unity and fill all inspector fields in the enemy AI component. Let's set the starting health to 100, the low health threshold to 50, the chasing range to 30, and the shooting range to 15. Also assign the player transform. Now assign cover spots in the cover component for each cover in the scene. Next, assign all covers to the available covers list in the enemy AI inspector and hit play. As you can see, the enemy starts to chase us, and if it gets in the shooting range, he changes his color to green, which means that he is in the shooting node. When we click several times on the enemy object, it starts to run to cover and changes its color to blue. If we wait long enough, the enemy will heal and stop looking for cover. There is one problem. Every time we move the player, the best cover might be changed, and that will lead to the enemy changing directions when looking for cover every time we move. To counter that, we will not look for best cover if the previously selected will still cover us from the player's side. So let's go back to the isCoverAvailable node, and in the findBestCoverSpot method, let's first check if there is a best spot selected previously. If yes, then we will check if that spot is still valid, and if so, we will return the previous best spot as the current best spot. Now when we hit play and make the enemy go to cover, when we change the player's position, the enemy won't look for another cover until the player is on the same side of the cover as the selected spot. Now let's wait for the enemy to take the spot. And now move the player to the same side, and we can see the enemy is running away. Let's also, in the update method in the enemy AI script, stop the agent when all of the nodes return failure. Let's put some more enemies in the scene and hit play again. There we go, full AI-based cubes are running around. So now that you have the knowledge about the behavior trees, I strongly encourage you to write your own custom nodes and create different behaviors. And that's it, guys. You can find the whole project on GitHub in the description below. I hope you enjoyed it, and please like and subscribe if you like my content. There are new videos every Monday. Also, leave a comment, I'm happy to answer all of your questions. Take care.